half of what we are going to do is actually going to help you in your dissertation, your thesis that you are writing. And you will see this. Because most of the things that make your thesis look good, fantastic, beautiful, and complete document will be half of what we shall be doing. So I would encourage you, please, to participate in the outworking of this document that we are going to do. Be participatory in it. It will help you. I promise you that. But if you only listen, it is not likely to help you as much as if you are participating. So let's begin. So by the end of this program, this is our objective. You should be able to separate exploratory data analysis, data processing, and descriptive analytics. They should be so clear with you so that when you are applying it to your thesis, your dissertation, you will be able to apply it with joy. Why? Because you understand it. You see, when there is an understanding, there is clarity. And when there is clarity, there is focus. Sometimes people pursue their dissertation and they cannot focus. And the reason why they cannot focus is not because of anything, because they are not clear exactly of what to do. They don't know whether they are dealing with imbalanced data or they are dealing with balanced data. They don't know whether they have to do test and split of their data. They don't know when to do exploratory data analysis, pre-processing. They don't know exactly when to do correlation and when to do regression, what kind of regression to do, whether lasso regression, whether range regression, whether elastic net regression, whether Huber regression, generalized Lee's model. They don't know. They are not so sure whether they are going to use support vector machine, random forest, decision trees, ADA boost, CAT boost, XG boost. They are not so clear whether to use Prophet or LSTM or autoregressive integrated moving average or what. They are not so clear. When there is clarity, there is focus. That's the point. And so this is supposed to help you to understand the processes you got to go through to be able to come out your way. Now, believe it, the research you are doing for your thesis, for your dissertation, you will notice, and if you haven't noticed now, majority of the work you are going to be doing is going to be centered on not just the literature review, but the methodology, and then the application of the methodology there, the data analysis. It will take a chunk of your work. And so all of these that we are doing will help you. So you should be able to view your data, know the dimension, know the missing values, know the data type, know the duplicates, in fact, next week you will see a lot of hypothesis testing. You will understand test and splitting of data, imbalanced data, how to handle it, smooth, how to use other, pre-processing activities, how to do other test and split, why 80%, why 20%, why validation should come in the middle and all of that. Then this will help you a lot to run your analysis. So let's begin. What is exploratory data analysis? It's a first step, the most important first step in descriptive analytics. You have to summarize, visualize, get some insight, discernment, identify patterns and trends, identify anomalies and relationships, and detect potential errors in your data. That is EDA. The goal of EDA is to understand the characteristics, the features, the structure of your data, check the quality of your data. In fact, I was going through one with one of my MSc students, and she said, look, I'm done with everything. I said, no, let's run this. When we ran it, she got to know that the data is imbalanced. She didn't even know that the data is imbalanced. Now she knows the data is imbalanced. She has to now use, an approach, SMOTI approach, to be able to deal with that imbalance, to balance it before she can now proceed. Else she's going to get wrong feature, importance analysis. So it's very important to uncover the links between variables, generate hypotheses before you proceed. Now, that is not the same as data pre-processing. You see, data pre-processing involves data preparation for modeling. Now, if you don't take it, sometimes it might look like it's an EDA. It's not, because you are cleaning, transforming, organizing, and doing feature engineering to the data. You want to improve the quality and make it more appropriate for analytics. What we are going to do today is EDA, but you should know the difference, because sometimes they can be overlapping differences, but here are the clear differences. Data pre-processing, the goal is to prepare, clean the data, and make it usable. But the EDA wants to understand the structure, the inside out of the data. Pre-processing looks more at cleaning, transforming, encoding, using one hot encoding or any other means of encoding. But the EDA will visualize, will summarize, will explore the data in that regard. Okay, those are the things that a person needs to be able to pick it up. Data pre-processing will use pandas and scikit-learn. EDA will be more using the pandas, the matplotlib, the seaborn, the plotly, and other things. But the key outcome is that pre-processing is ready for model dataset, whereas EDA has to do with bringing knowledge and hypothesis to bear with the data. So we're going to look at a couple of these by taking the heart failure prediction dataset, which all of you have it. Please, if you have the data set and you have opened your Jupyter notebook, just as I've opened it here, just raise your hand. Please raise your hand so that I'll be sure the sort of about how many people I'm done with. Okay, so I've got approximately, let me see the number, approximately a good number of people, about 12 to 15 people who have indicated that they are moving along with me. As long as I have at least 2, that's enough. So let's set the ball rolling, okay? And you will benefit a lot as you go through this. Sometimes the tendency is that, I'll look at the lecture slides later. You can lower your hands down. I'll look at the video. I'll watch the video. Look, you don't have time. You don't have time. You will see that sometimes you watch it, you won't get time to watch it because you have so many things running around your life, you don't get time. So sometimes you just participate. The time you are here, you participate and be free. All right, let's look at a heart foundation prediction data set. Now, this is cardiovascular disease is very common disease, can cause a lot of death across the world, 17.9 billion lives every year. That is 31% of all the deaths in the world. 4 out of 5 cardiovascular disease deaths are due to heart attack and strokes. 1/3 of the deaths occur prematurely in people under 70 years of age. 1/3. So don't think that is only for the old people. Heart failure is common. And the data set we are going to deal with contains 11 features, 11 independent variables, 11 features that can be used to predict possible heart attack. People with this disease or who are at high cardiovascular risk because of the presence of one or more of the factors like hypertension, diabetes, hyperlipidemia, or already established disease, genetic diseases, they need early detection and management. And machine learning can help. So the data set you're about to see, the goal is to use it to determine the likelihood of heart attack. And a lot of people in the health sector and several places coming. Now that word, the likelihood of heart attack, is a binary classification environment that we are in here. It's the same as when you want to take a logistic regression analysis. And of course, you want to do random forest or any of the gradient boosting techniques, whether it's cat boost, it's ADA boost, or it's XG boost, or light GBM, they all, will have things like that. Where the categorical variable, the dependent variable, the target variable is binary. This can go to those of you who are doing fraud detection, those of you who are doing churn prediction, those of you who are doing loan default prediction or stock gold price prediction, the same thing. So I think in the case of gold price prediction, you are dealing more with continuous variables. So it's not that discrete binary. So let's go back to the data set and look at the factors that are likely to determine the probability of having a heart attack. One, age. Age is critical. And you will see in the data set very soon that the ages are ranging between 28 to 77. Sex, whether the person is a male or female, is a key characteristics. Chest pain. This is a whole thesis, by the way. See, one of the critical things in your work is getting your data ready. I would love it. I want to love it that you tell me that, look, my data is ready. Yeah. You are smooth sailing. 60% of your work is done if your data is breathing right now. The kind of analysis you can do, chest pain can determine that, okay? And the chest pain are 4 different kinds, okay? Whether you have typical angina, atypical angina, okay? Whether you have non-anginal pain or you're asymptomatic. Okay? These are 4. Then you can have resting blood pressure, okay? Which ranges between 0 to 200. 0 is likely an error or a missing value because you must have something. You must have one of the values. Number 5 is cholesterol level. The serum cholesterol level ranges between 0 to 603. And 0 may again indicate a missing data. Now, why am I walking you through this? I'm walking you through this data because you got to eat your data. Sometimes you get your data is ready, but you don't know the nitty-gritties of your data. You got to know the inside out. You got to eat the content of your data. You must understand fully your data. When a supervisor asks you, tell me about your data, you should be dancing, because you are so powered up to want to educate your supervisor about your data. Know your data fully. And this is where you will take this data set, for example, and take it to the appendix so that the reader will understand in your thesis. Fasting blood sugar level. Okay. If fasting is bigger than 120, okay, diastolic, then you know that, and that is given a value of 0. Otherwise, it is not given a value of 0. So you have one that is 120, more than that, or one that is below or equal to 120. Then the resting ECG, okay, the electrocardiogram result. Okay, that one is also in the kind of levels. Normal, ST, having ST, okay, T with abnormality, and all of the other different ones. You see that in the data set. The max HR, the maximum heart rate achieved, is a numeric value and ranges between 60 to 202. Whether the person has been doing a lot of exercise so we can take the exercise angina, exercise-induced angina, well, it is a binary variable, which is either yes or no. And then the old peak, okay, which is a ST depression induced by exercise relative to rest. Now, if you don't understand some of this, no problem. It's not in your area anyway. But some of you are in the health sector, you understand this, and the medical professionals, you understand it, that's okay. Everybody who is doing a research fully has to understand the industry in question. It's a numeric variable. It's measured with depression. And then you have the ST slope, the slope of the peak exercise. Okay? Up sloping, flat, down sloping, 3 levels. And then the bottom itself, the target variable, the number 1, okay, which is binary in this case, a heart disease. The output class is 1 if the person has got a probability of having a heart disease, 0 if he's got a probability of not having a heart disease or having a normal heart. The data sources actually was combined, is available independently, but not combined before. Okay? In this data set, 5 heart attack data sets are combined over those 11 common features we've shown here. And they make up the largest heart attack data set available so far for research purposes in the world. Now, the sources are Cleveland. We have 303 observations from there, Hungarian, okay, 294, Switzerland, 123, Long Beach, 200, and then you had Starlog data set, 270 observations. All of these have been combined, generating 1,190 observations. Okay, some of them were duplicated, were 272 observations, and the final data set, because of the duplicate, came down to 980. Somebody says, is a heart attack also part of the 11 attributes? No. That is why you see that the heart attack is number 12. It's not part of the 11 attributes. The attributes are the features that can determine the probability of heart attack. Heart attack is a target variable. It's not one of the attributes. So that's. Now, anytime you are citing the data, you use this citation. And you can check the data source actually on this page. Okay, ladies and gentlemen, let's begin. How do you do exploratory data analysis on this? Number one, before you model any data in this world, the first thing you got to do is to identify whether there are some issues in the data. Pre-processing would then, after the EDO, pre-processing will have to be applied on the data set to fix identified issues. But the first thing we're going to do is to perform the exploratory data analysis, after which we'll do the pre-processing. So one, let's load the packages needed. NumPy is very common. You need that all the time. Pandas, you need that all the time. Okay, these are clear, data manipulation packages. Then a couple of visualizations, Seaborn, Matplotlib are very, very common. Then the possibility of, here we can just ignore this, but you will later realize that if you have to ever build linear regression model, okay, then you will load that. Okay, stats model is not normally good when you're building linear regression model, making it look like you are doing it in R software. Because when you are actually doing linear regression model, okay, and you are building, you use scikit-learn usually. However, scikit-learn is not able to beautifully showcase the thing the way it is supposed to be shown, the way sometimes even Excel will show it. So this task model is very useful because it's a kind of an embedded R package inside Python that you can call for it. I brought it here just in case. And then, of course, scikit-learn itself is also here. When they need in subsequent ones, when we are doing standardization, normalization, we will use all of these packages from scikit-learn. Okay, so let's load this data. I'm running mine, you should run yours. We're going to call the data set DF. Okay, that's it. You're going to load the data set and call it DF. So click inside here, okay, and we are going to write a command that we will use to call the data set. So you should be typing whilst I'm doing the same thing. How do you call the command? Let's call it DF. So you write DF equal to, then we load the data set. This is a CSV file. So you write pd dot read, okay, underscore CSV. That's what you're doing. Okay. And then you write the name of the data. It says call hat. Okay. So into brackets, write your hat, because that's the name of the CSV. Put it in single apostrophe. That's the first thing. Now let's show the first 3 rows of the data. I've indicated a command here. Okay. To show the first 3 rows of the data, how do you do it? You just write df, which is the name of the data, show the head, into brackets, and then you write 3. You can do 10. Let me do 10. Okay. So instead of showing the first 3 rows of the data, I want to show the first 10 rows of the data. If you are lost, let me know. Let me know now, not when we have gone so far into the sky. Any questions so far? All right. So let's run the data and let's see the results. The results will show here if you have run it well. If there's a mistake, it will also show there. So as you can see, there is an error. So let's quickly check the error. Okay. So you have DF.
So you have to add the CSV to the hat.
It's true. Oh my goodness. Dot CSV. Good. So you can see that some of the variables are categorical, like chest pain is categorical, like sex is categorical, like resting. Resting BP is not categorical, it's float. Okay. Cholesterol, actually, it's not even float, it is integer. Okay. Cholesterol is integer. Fasting, BS, okay, it is integer. Resting is object and therefore it's categorical, and then on and on. If you look at old P, that is decimals and therefore it's slope. So you've got a lot of varieties of variables that are here. Next thing to do is to find the dimension of the data set. Okay. Now, what does the df.shape return? Who can tell me? When you do df.shape, what does it return? What does it give you? If you do df.shape, okay. Now, if you do df.shape, it's going to give you the rows versus the column, the number of rows versus the number of columns. To do that, okay, run that. You have the number of rows versus the number of columns. Okay, so the number of rows are 980, the number of columns are 12. Remember, at this stage, we've included a target variable, which is a binary dependent variable, which is the heart disease. You have that there. You see, if the data was not there, then we have nothing. So that's why your data must be ready. The data must be ready. Okay, next thing. Once you have your data, so these are all EDA, exploratory data analysis. Check whether they are missing values. Evaluate the data set. Check whether they are missing values. And an easy way to check whether they are missing values is this command here. If you use this command, is null dot values, check if there is any values that is empty. It will tell you whether the data set has got a missing value. It will return true or false. Okay, so let's run that. I've just put that one there. And then it says false. False here means that there is no missing values in this data set. No missing value. No missing value. Okay. If you are running it along with me, fantastic. Now, how is this command, df is null, blah, 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 blah? How is it different from df is null dot any? This is a very important one there. How are these two different? Now, if you check df is null, okay, dot any, it checks per column. So you give it a series of a Boolean for each of them. But then if you take this second one with the values, it actually checks the entire data set at once and it will turn a single Boolean, just as I did for you. So take note of that. I have another question here. These are all kind of examinable questions. What is the output of DF? Okay, if the data frame has no missing values. The only answer you get is what? False. You just saw that here. It gives you a false. Now, what if it has a missing value? How would you handle missing value after you've detected that they are there in your data? And you got to check, guys. How do you do that? Now, for some of you, in case you don't know, you know, I'm sure you know by now, that you have to check whenever you are working these things and you are lost. Somebody say, how do you know which code to do? Whatever code you are going to do and you are stuck, you can ask Claude AI, Claude AI, Claude AI. You can ask Chat GPT. You can ask DeepSeek. Note these three down. Don't always use ChatGPT, ChatGPT. Okay, these three. Okay, use them along. Don't do it in Google. That is way out of line. Don't go down that path. Okay, use these ones because it will give you better things. And of course, you got to verify and make sure that you're on the pathway. Okay, so the first thing you got to do if you identify missing values, and me, I don't encourage this first one. Drop the rows and that column that have got a missing value. Imagine that you have a particular value. In fact, today I was working with somebody and the person is having 12,000 observations. And we realized that one particular column has got missing values and the missing values there are 8,000. So you're going to drop this, these rows, every section of the 8,000 you're dropping it, no way. Now, when we checked it, we got to realize that they have all been represented by none, N-A-N, N-A-N, N-A-N. And when you check it carefully, you realize that it is the same thing as the previous ones. So those N-A-N shouldn't have been N-A-N. For example, I'll give you a typical example. If you have sex type, okay, there's a way you can detect, even if you don't know the sex type of a particular individual in your data set, you can look at the other variables and you'll be able to check what is happening with this. And we were able to fill in every missing value. That's one. The other one is you replace the NaN with 0. Again, I don't buy that. The other one is to interpolate, fill the NaN with an interpolated value. I buy this. You can use forward fill, backward fill to do that. But the key point is that handle that. The last resort is you remove that row or that column. But what if that column is very, very important? What if that column is your key independent feature that you are looking for? Okay. Suppose you want to look at the probability of having a heart attack, and your main factor is age. And you're going to drop that column. Then you have no story. So that's why it's always good to address it properly. Next, check the data type. Okay? There's a command you can just use to check the data type. It will help you to have a feel of the data type that you are actually dealing with. How do you check the data type? It's very simple. Click here and type DF, that's the name of the data, and then do D types. Okay? DF, D types. That's it. And then once you run it, it will tell you the data type. Let's run it and see. So you can see that it will tell you that age is an integer, sex is an object. An object here means it's categorical. Chest pain is an object. Resting BP is an integer. And then blah, 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 blah. And then old peak is a float, which means it's got decimals. And then ST slope is an object, which means it's a categorical variable. And then finally, your disease type is an integer. It's actually a categorical variable, but it's been coded as 0 or 1. Okay, as you can see it from here, the last column is being coded as 0 or 1, 0, 1, 0, 1, 0, 1, and so it sees it as an integer. It's actually a discrete variable, or a binary discrete. Okay, so that's it. Now, why would you love that the data is more integers, is more numeric? Well, the good thing is that if they are numeric, it's good. You can do a lot of arithmetic calculations on it. The mean, the median, the mode, the standard deviation. You can aggregate some variables, group by operations, generate some pivot tables. Most of the statistical tests, the machine learning algorithm, t-test, regression, correlation, neural networks, long short-term memory, ADA boost, or SGT, all of these, okay, is good when they are numeric. Okay. Also, you can do a lot of plotting libraries with them. Okay. Most of them require the data to be numeric. Even categorical variables like low, medium, high, they often need numeric conversions. So you can encode them. You can do one hot encoding and say that low is 0, medium is 1, and then high is 2. So numericalizing the data, numericalizing the categories is very important. And still, you don't lose the meaning. You don't lose the meaning one bit. Now, let's look at chest pains. Okay, if you look at chest pains, okay, and of course, you can look at it at the data types here. Chest pains. It's an object. We can numericalize it. Okay, it's non-numeric, and we can numericalize it. How you do that? There are several approaches, but an easy one is one-hot encoding. Look at that later when we are getting to the real machine learning building. The next thing is to check for duplicates. So we can use this command to check that, is my DF data having any duplicate? Okay, if you run this command, it will return a Boolean marks. That will tell you, whether there are duplicates in the data. If there are duplicates, show it. If else, then you will get a print, okay, whether the duplicates exist or they don't exist. So this print is a statement that will give that will be returned if there are no duplicates. And then, of course, if there are duplicates. So let's see. So this return here says that there are no duplicates in the data. That means you are good to fly. There are no duplicates. Now the question again is, what if there are? Well, if there are duplicates, it means that there is a ton of redundancy there. So you got to address it. You got to address that redundancy. Are you clear? Are you guys with me? If you can hear me loud and clear, type yeah. Yeah, there, right? Because this is going to help you. It's going to help you. Yeah. It's going to help you with your work. I wish you have your data. I'll be using your data set to be demonstrating all of this. Yeah, I like the yeah that some of you are typing. Okay, let's check whether there are inconsistencies in the data. Now, if you have categorical variables, and they are troublesome with these guys, these categorical guys, you have to identify any incorrectly written, because sometimes you're writing male, female, but then one of them you wrote males. Hey, males. That will generate the levels to be no longer 2. Just because of that typo, you have 20 million observations. And then at some point, you made males. At some point, you made females. Instead of male and female. Now you're going to have 4 levels. So when you check the categorical leveling for every variable, you're going to get 4 levels. So if you are creating dummies, you're going to create 4 dummies instead of just 2 dummies, simply because of typo. Simply because of typo. So you got to check for inconsistencies. You'll be punished. The machine learning algorithm is data dependent. You'll be punished. And so you got to make sure, step by step. And I was telling somebody that don't delay getting your data. Don't say, well, I'll get my data. See, you can spend a whole time period cleaning your data, analyzing your data, doing a lot of things with data engineering. So it's important that you get your data. Get it. Get that data ready. Get that data ready. Get that data ready. You don't have time. Get that data ready. Okay. So you identify any wrongly written, misspelled, repetitive data, okay? And you can use for loop to check the uniqueness of each category. For loop is a very, very interesting thing. Okay? So when you type 4-column in DF, okay, you are trying to use the for loop to check the uniqueness. Is there uniqueness in my data? Is my values unique? Okay. And if they are unique, you will check the unique values of each categorical variable using a statement, because the categorical variables are not that unique. So you want to use a code to check whether the categorical variables are unique by using that if statement. And then after that, you can print your result, okay, the unique values for every column. You check for every column. Let's do that. Okay. So this is what it means. So these are the categoricals. That's our focus there. They are the troublemakers. So you check size, sex type. Sex type, it will tell you that the levels are what? Male and female. Now suppose he has told you that the levels are something else, FS. Then it means that you should go up there and go and correct FS, because it's not supposed to be, FS. It's supposed to be what? F. But you made a mistake and added S to it. So it's created another element. Chest pain. You have ATA, NAP, ASI, TAs. Imagine he brings another one, TAT. He said, what is that TAT? But you see that because the data is plenty, you don't even know that there's TAT in the list. But here, it will bring out everything that is in there. So that in case, when it gets to the time you are going to encode them, you do not make a mistake to think that these are 5 levels, when in reality, they are just what? 4 levels. The rest in echocardiogram, you can see that that one is what? Is normal, ST, and LBH. exercise angina is no or yes. But if you've made a typo somewhere, it will bring it out. And once it brings it out, you're in trouble. So this will pull out those things. They are the noisy makers. Okay, I've got a question here. Doc, I've realized that when you are removing duplicates, the values that are duplicated are all removed without maintaining the original. I think that is a loss of information. Of course, so you don't have to remove those duplicates. There's a way you can remove just the duplicate itself on its own without affecting the all of them. Okay, you can encode it in such a way that it will remove only one or those that are duplicated and leave the ones that are not. So if you want only Kweku in there, and Kweku is appearing 16 times, you remove 15 Kweku and you've left it one. You can do that easily. All right. So from this output, you notice that there does not appear to be any inconsistent values in any of the categorical columns. Of course, if you know what you're looking for, then you know what you're looking for. You have it all. Great. Next, data distribution. Now, what is the distribution of the data? The distribution of the data is just how the data looks like. Just how it 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 looks like. The distribution is blending the central tendency with the spread. Blend the central tendency. The central tendency is the mean median mode. Write it down if you don't know the mean median mode. So how does the mean median mode juxtapose against the spread, the standard deviation and the variance? When you match that, so it's not just telling you the shape. It's not just telling you the center. It's telling you both the shape of the whole thing. You are getting the maximum. You see, the central tendency is just telling you the mean median mode. But it's not telling you anything about the quartiles. It's not telling you anything about the maximum and the minimum. But the distribution is telling you everything about the data. So you got to evaluate the balance of the data, especially the target variable, the main variable. Okay, very important. So that there are no biases in the data, especially when you're doing binary classification analytics. So you got to know the frequency of each class. In the target variable, we have the probability of getting a heart attack and the probability of not getting a heart disease. Know the distribution. Check whether heart attack has got that, okay? So one way you can do that is plotting. And use that plotting, even use some red colors and blue colors to show, tell me those that have heart disease, tell me those that don't have heart disease. Okay, Matplotlib will do that very beautifully. So first, you got to convert the heart disease. If it is an object, convert it to what? Numbers. And then you can now use the count. So you use the count. I like to put the numbers, the frequencies on top of the bins, the graph. And then add, so here I've said that add frequency count on top of the bars. Okay. And then iterate over each of the bar in the plot and annotate it, add a text and everything. So you do that, you run the results so that you can have what? A beautiful graph like this. So in this count, you are able to see a lot of beautiful information. First of all, you know that 1 is a likelihood of having a heart attack. 0 is the likelihood of having no heart disease. You'll be able to also know the count, which has been put on top of the values. You see, just having the count on top of the values alone is this whole thing, this whole coding. This whole coding. And again, when you look at it, you see it. But if the coding wasn't there, I wouldn't have to do it. Because even here, it tells you that you want the number to be in the center. So if you look at both of them, the 508 is in the center of the bin. The 410 is in the center of the bin. Okay. And then the alignment is in the vertical alignment. So all of these things are positioned. Of course, when you're using the 3 things I told you, they can guide you when you are doing this code. Anytime you are lost, don't say that, say I'm lost, say I'm lost. No, you got Cloud AI, you've got ChatGPT, you've got DeepSeek, you've got saving more that can help you in the process. They are helping you. They are not doing for you. So you got to run it. They might guide you with the code, but you have to come and run the code yourself and see it with a physical eye, so you are able to understand what is happening. So based on this, what can we say? We can say that the likelihood of people having heart attack is more than the likelihood of people not having heart attack with this data set we have. Why? Because the probability of having a heart attack is 508, and the probability of not having a heart disease is 410. So in this data set, so you are able to get a feel of that in the first place. Now, the question we got to ask ourselves is this data balanced or imbalanced? Who can tell me? Is this data balanced or imbalanced? Who can tell me? Is this balanced? Oh, all of you, you will have to determine whether your data is balanced or imbalanced. Every one of you. It doesn't matter what you're doing, whether you're doing continuous or discrete. Is this data balanced or imbalanced, and why?
So there is class imbalance situation.
There's
Because
class imbalance. Are you sure? I don't believe it.
The 508 far, outweighs the 410. I mean,
Are you
maybe
sure? I don't believe it.
maybe you may. I want a more perfect balance. Maybe Smart or Anderson can do a better job. I don't know, but
because there's a bigger issue if it is 90% against 10%. That is a lot of imbalance. Now, if you want to do, you can just check the percentages. Add the two together, divide by each one. 508 divided by 918. Multiply by 100. You can do that on your calculator right now and check. And actually, you can actually command it to do it for you. But since you are talking, you can do that. 508 divided by 918 multiplied by 100. What do you get? You're not even going to get more than 80%. It's not even 80-20. It's not even 70-30.
It's most likely to be 50.
Oh, no, please. Just calculate instead of saying most likely. Come on.
55.3%.
Look at that. Against 47 point something. Or 46 point something.
Yeah.
It's not too significantly removed.
Right.
Yeah. Okay. We're not talking about perfect balancing. We say that, near balancing. And this one is near balanced than near imbalanced. Than even talk about its imbalance. Yeah. So take note of that. Anyway, somebody has a question. Doc, what if you have a variable like location that has around 7 to 100 different unique values? What is that? I don't understand that question. I don't understand. Okay. All right. So that is it. So let's look at it. So you can calculate a percentage. I've even brought it here. You can calculate a percentage. So what percentage of each class has heart disease? So that number you spoke about, that is it. When you run it here, 55.34% patients don't have heart disease. And then 44.66% of the patients have got heart disease. Okay. So I have the question here. Yes, Amanda.
Doc, please, I think the narration has been mixed up because if one is heart disease, one is higher. So I think the 5.5 should have the heart disease and 4.4 is do not.
Oh, yeah. It's a typo. You are right. Oh, the percentage is here. Oh, but hold on. Maybe I'm even making my earlier mistake myself. Let's check the data set. Okay. 1 is heart disease and 0 is not. Yeah. So 1 is heart disease. Okay. Normally that's how it is. So I've made a typo here. So percentage of patients who have heart disease. Okay. Percentage of patients who have heart disease. So you should check it in yours. I'll correct it. And then there's a percentage of patients who do not have. You're right. So that's a typo. So 55% have heart disease now, and 44 don't have heart disease. Beautiful, beautiful. So in the target variable, I put here is the data, is the disease imbalance. Okay. And I've indicated a severe imbalance typically is when the one class is 90% more. Okay. Now ours is 55%. That's severe, that's severe. Moderate is 70-30. So moderate is 70-30 to 90-10. That is serious, okay, 90-10. But our case here, 55 is not considered significantly imbalanced. Okay. This level of imbalance is mild and generally is acceptable for most machine learning models. In our data set, the target variable is made out of 55% of the data in one class, 45% in another class, indicating a relatively balanced distribution between the classes. Therefore, you can apply a method to balance the data that may be unnecessary to use. Like I said, one method you can use to balance the data is the SMOTI. Okay. Do you guys know about the SMOTI? Who has been teaching you supervised machine learning model? Do you guys know about SPOTI?
Look, me, I don't know.
You don't know. Who knows about SMOTI? It's a very, very common approach. Synthetic minority oversampling technique. Won't take that wrong. Synthetic minority oversampling technique. Okay. Yes, Asante.
Yeah, I know about that, and I know about the smart in, and I know about Anderson. I've read about it.
Yeah. So you should start thinking about it. You all have to check your data set. And for those of you who are doing a lot of binary classification, most of the binary classification analytics have imbalance. Guaranteed. So you should check it. Okay. All right. So because anytime you're doing logistic regression random forest, okay, they will handle this very one easily because it's not having imbalance. Only worry if the minority class is critical. Okay. Fraud detection. I gave you an example, rare disease. Even small imbalance might need attention. Okay. Now here, even though there's not much of an imbalance, you can still decide to balance it. It's a very, very simple approach. So simple to use to if you want to balance it. Oh, it's so simple. It's so simple. The SMOTI will do the thing, and they will tell you that all of them. You see, one of the things it can do is that you can use two approaches. One of them is you can use oversampling. That's what the SMOTI is using. It's using oversampling, which means that you take the minority class and create a synthetic values for the minority class. That is, the minority class, you increase their number. That's it, you increase their number. Or you can do undersampling. Okay. The undersampling is where you take the majority class rather and cut down their number. Which one do you normally like? Which one do you think you in Africa you normally like? The oversampling and undersampling.
Oversampling, sir.
Yeah, why?
Because most of the time our data may not be enough, and
Exactly.
oversampling, you generate synthetic data. If you undersample, it means you are going to delete some of the real information you have. It doesn't really make sense.
Super. That's it. That is exactly the thing. Okay. Next, data preprocessing. Let's get it rocking. Now, after you've applied the EDA, you may see that the data set presents several issues that may need to be fixed. What are some of the issues? Outliers, non-numeric variables, slight imbalance. Now, you got to first of all check for outliers. What are outliers? Who can tell me the difference between outliers and influential observations? Outliers and influences. Outliers are abnormal, but they do not influence. Okay, you see, for an outlier to be influential, so all influential observations are outliers, but not all outliers are influential. I can show you an example, but maybe there's no time. I'll give you just 3 data sets. So this is one data set. This is another data set. This is another. Okay, let me put it here. This is another data set. So when you look at this, and you look at the environment of this first two, and you see this is an outlier. The third one is an outlier, but it's not an influencer. Why? Because when I throw a regression line through this, it's not going to drive the regression line from the mean. But suppose that I rather have another one here. You see, this one here is also an outlier, just like the one at the top. But if I want to throw a line, because this one has deviated from the line of best fit, it will, instead of the line probably going this way, because this one is already on that line, it will rather go probably that way, okay, because of this guy. So this guy is an outlier and also an influencer, but this one is just an outlier. Just take note. So when you have an outlier, it's a problem. They are deviating significantly from the majority of the data set. Unusually high, unusually low, compared to the rest, can bring a lot of statistical discombobulations in the data set. So you got to check it. You got to check it. They actually define based on measures of spread and the distance, using the standard deviation, using the variance, using the interquartile range. But categorical variables, they represent a discrete group. 0, 1, 0, 1, 0, 1, 2, 0, 1, 2. Okay, or they do that discrete or labels. So they make traditional outlier detection very irrelevant or misleading. So we don't really look at that. So it's important to check for outliers in the numerical variables, not in categorical. Okay, so outliers are done for what? Numerical. Why? Because numerical variables have got multiple items to deal with, not category, not discrete groups. So how do you check it? First, use box plot. And I know you guys have done visualization, so you know about box plot. If you don't know box plot, you raise your hand, I'll explain it and draw it for you. Okay. Now, so in the one we're about to check here, we are going to check which of them have no outliers, which of them have got the most outliers, and which variable shouldn't have even been included, and why. So we're going to look at the entire data set. Okay. I'm going to import Seaborn and Matplotlib. We're going to plot the box plot of all the numeric variables, not the categorical, numeric. So how do you do that? Just plot this. Run yours. And you will see that it's going to show the box plot of the numeric variables. So look at the variables now. Age has got a probability, has got a chance of, bringing about heart disease. Resting blood pressure, cholesterol level, fasting blood pressure, okay, max HR, old peak, all of them. Question. Which variables have no outliers? That's the first one. You can tell us. Which variables have no outliers? You can tell us. Let me see if you can remember some of the variables. Good. Some of you have written age. Age is obvious, okay, that age has no outliers. Now, one thing you can do is that there are other ways you can check the outliers. This is another plot which I've given you that you can use to also check for outliers. It's another way, okay, where you can put the box plot inside the boxes. Again, you can see that age has no outliers. But even more powerful is that you can tell the numeric variables. This is where your answers come. Okay. So this command would define the possibility of detecting an outlier one by one, numerically, not just graphically, numerically. Then it will pick on each variable. Oh, I made a typo. Okay, so you're supposed to define the stats. Did I not define the start here? Let me see. Oops. So it's good. It's good we have this typo. So let me show you something. Okay. Let's say that you've had a typo like that. You're running the model. You've had a typo like that. Okay. How do you handle it? Let me show you something interesting. I'm just going to go to here. DeepSeek. Okay. You've had a typo here. Actually, it's not this one I'm supposed to do. You can copy the error and then request for support. And I know most of you know about this already. So let me just stop this. And just request for what mistake you've made, you know, and it will correct that mistake. And then it will tell you what you actually had it wrong. Because I think I should have installed something. And then you can check it. And then you can run that again to ensure that there are no issues. So let's go back here. So you take that command, because I was supposed to probably add some stats, okay, this one, which I didn't import. So I now import it, I run it now, and then it tells me the answer here. So now you are able to know outliers per column numerically instead of checking. So now you can see that, okay, it's not only age that has no outliers, but what? Fasting BS also has no outliers. Now, if you check fasting BS, it looks like there's some sort of outliers there. It's not an outlier. Who can tell me why that dot is there? Yes, Amanda.
Doug, sorry, please, can you scroll down? I didn't see the correction you made.
Okay, this is it.
Okay, thank you.
So if we check fasting on the graph, it looks like there's something there, but it's not something. It's because it's a dummy variable, which has been coded. Okay, it's been coded, sorry. So sometimes some of the coded values might make things look like, you know, it's an outlier, but it's not an outlier. So just so you know. Fantastic. So now you can see that which variable is a problem child when it comes to outliers here. Which variable? Graphically, you can see, but which variable? You know, when you look at cholesterol, it looks like cholesterol has got a lot of outliers, but it doesn't. Okay. Well, numerically, it is showing here cholesterol has got just what? 3 potential outliers. Okay, so the key point, so you should edit the work that you've been given, edit it. So which variables have got outliers, click here and then edit and write it there. The first variable is what? Which variable has got no outliers? Age. Which variable has got the most outliers? The most outliers.
Resting BP.
Resting BP, very good. Which variable has got, what's the next one? Shouldn't have been in the model. Actually, the one that shouldn't have been in the model is not in the model. Okay. I think in the previous one I ran, it was in the model, but this one is being removed because I had added, okay, actually, let me show you. Look at fasting BS. So somebody's a resting BP. A resting BP, look at resting BP. It's got 8 outliers. Okay. So that's not it. Okay. But we'll go and check the variables. I want to show you something. We're going to, okay. So look at fasting BS. It's got values of 0, 1, 0, 1, 0, 1. And when the thing has got a values of 0, 1, 0, 1, 0, 1, obviously they are just dummies, but they've been coded. And that's why they were numerically included during the box plot visualization. So that is the one that, this is an exam question, so that's why I'm asking you all of this. So that is why it's not supposed to be included, but it's been included here. So when you look at fasting BS, okay, it's been included, but that is why it appears that there is no outlier. Of course, there shouldn't be an outlier because it's just two variables, 0, 1. Kind of dummy, binary, like heart disease. And so ideally, that should not be included. So it is the one that should be included. Okay. Now, how would you identify outliers using the box plot? We've just done it. One easy way you can identify outliers using box plot is take I'm talking about how it was identified at the top. You took 1.5 times the interquartile range. The interquartile range is actually the third quartile minus the first quartile. Yes, Amanda, your hand is still up.
Doc, so please, I have a question going back. So if you look at the old peak column.
Good. Let's go back to old peak. Yeah. The first
Looking
one.
at it, can you also consider that one as not being valuable to the data sets?
No, because when you look at it carefully, there is a box there, isn't it?
Yes, but looking at the data, it's just a 1.5, 1.5. It doesn't have a lot of, the rest are zeros.
The bigger picture is not exactly what you are seeing. So sometimes I bring another one. So you can see this second one here. That's the same old peak. What do you see about old peak here? Let me run this again. Maybe I haven't run that one. Yeah, the same thing. What do you see about old peak?
So old peak has the minimum value at 0. Okay, no, it's ranging from -2 to -4
Old peak is 7. Look at it.
for the outliers.
Yes, outlier per column. Old peak is 7. That's what you see here. Look at the numbers here.
Yes.
7. Please, do you understand? If you don't understand, I can explain further.
Please explain further.
So what I'm saying is that, first of all, we wanted to know which variable has got no outliers, and it is age. Now, age is sensible to be included as having no outliers. Why? Because age is in a number, is numerical. And how do we know it's numerical? Because when you look at the box, you can see that the box is there. This is a box plot. When you look at the box here, the box is there, it's there. But there are no outliers graphically. But the number is even telling us that there is no outliers, which is 0. So it's numerical. Fantastic. Hallelujah. Now, there's another variable that is also 0, which is fasting BS. But fasting BS is not numerical. So why was it brought? Because we were not requesting for categorical variables. Well, because we had coded it. You see, it is a categorical variable. That is why fasting BS, when you look at the box, okay, the fasting BS box is just flat. What does that mean? It means that value is just 0 or 1. That's it. It's just 0 or 1. And if it's 0 or 1, it simply means that it is binary. And binary, you don't need to look at what? You don't need to look at outlier for binary. Why? Because outlier detection is for numerical variable, I'm talking about numerical continuous variable. Outlier detection is for numerical continuous variable. Take note. And fasting is not. And that is why it is reflecting here like that. That is why it is showing 0. So the 0 here doesn't mean there are no outliers. It's not even supposed to be there in the first place. That's the point. However, when you check old peak, okay, when you go and check old peak, when you look at this first graph, it looks like it's looking like fasting BS. But old peak is actually numerical. It's not binary. It's not discrete. How do we know? Well, you can go and check the values. Okay. Let's go and check the values. And you can see old peak here. You see, they are numbers. You have 1, you have 0, you have 1.5, you have decimals, you have some values for it. So it's actually numeric. But when you check fasting BS, it's 0, 1, 0, 1, 0, 1, 0, or 0, 0. Okay. So that is why. In fact, if we look at the head of the data, let's look at the head. Let's look at the whole data. Let's look at the whole data. So you see now, this is the entire data set, 918. When you look at fasting BS, it's got 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, all through. So it's what? It's binary. Just like heart disease is binary. If I had drawn heart disease as part of the whole thing, I was not looking at heart disease because it was a target. I was looking at the features. If I had included heart disease would have been one of the variables that you don't need to check for its outlier because it's binary. But when you look at old peak, now that you have the full data set, look, some of them are 1.2, 3.4, 1.2. So it's numeric. It's numeric. It's numeric. It's numeric. And therefore, old peak cannot be classified by looking at outliers. Amanda, do you get it?
Yes, I get it now.
Okay, Solace, your hand is up.
Yes, look, I was just thinking about the whole box plot. If the box plot is supposed to show us our outliers,
It's not supposed to. If it's not there, it's not there. It's not supposed to.
okay,
It's like going to check for cancer and you say that the checking for cancer is supposed to tell us that there is cancer. It's not supposed to. If it is there, it will show. But it's not supposed to show.
okay. So, okay, Doc, understood. But my point is, the visualization is supposed to give us an idea of what the
Good.
data is
A
saying, right?
feel. Good.
Okay. But then looking at the box plot visualization, it's the whole thing. Okay, for old peak, let's look at
Good.
old peak and resting BP.
Yes.
Old
That's
peak.
2 boxes. So whilst you're looking at the first one, look at the second one too.
Okay, so why would we have to look at the second one if the first one is supposed to speak to us? That's my point. It's like the visualization is supposed to tell you something, but it's not telling you.
You're right. Oh, you're right. Why is it that we have to check the possibility of going to Accra with aeroplane if there is a bus? Why do we have to check the possibility of using a motor or an aeroplane if there is a bus that can also take us to Kumasi? Life is full of varieties. Why are there blacks and whites? Why should that be a problem? It's variety. Why do you paint a corner of your house white and another corner of your house, brown or ash? Variety. Yeah, variety. God loves variety. We are human beings. We like variety. Why is it that the same car, the same BMW, you paint sometime red, another one blue, another one, turquoise blue, another one green, another one black, another one. Why? Variety, variety. So you asked me the question, why should we have this box plot? You don't concentrate on one. That's why I give you other one. And I even go ahead to show you the numbers to help you to have a confirmatory decision to make. So, Liz, are you following?
Yes, Doc.
Okay. So you get it. So you have to use all the possibilities to come out with a conclusion. In fact, that's the same thing you would do when you come to the machine learning algorithm. Why do you have to run random forest if there is ADA boost? Why do you have to run SG boost if there is cat boost? The same thing. Variety. You want the best. If we had focused on only the first graph, we would have gotten the best. Okay, this was there before. Then there was another way to look at it, and this came. Then there's another way to look at it. Then the numbers actually came. Now we get better. We are failed. We are fulfilled because we are failed. Okay, now, so you can use this. So the way to detect the outliers is this measurement. So what is actually happening is this measurement. Okay? This measurement is actually this final running. I've just run it to show you. I just did it for cholesterol. This measurement is actually tell you the calculation. Okay, it's a little bit detailed. I can look at it, understand it fully later. But it's just to tell you what was done to actually find these numbers. It's just to give you an idea. Okay, I'm not going to go too much into that. Now, if they are outliers, what do you do? Like the ones we have, if they are outliers, what do you do? Remove them. Well, one common thing people like to do is to remove them. But there must be a very strong basis to remove them. Okay. Now, if you want to remove them, you got to run the work again. Use the interquartile range method. Especially if your data is not normally distributed, use that one. But if your data is normally distributed, use the z-score. Take note of this. This is an examinable question. Which one do you use to handle outliers when the data is skewed? Which one do you use to handle outliers when the data is not skewed? So here, again, assumption. I'm assuming that the data is normally distributed, even though I don't believe it is. Okay, of course, you can check the distribution using the Shapiro test to check one by one. Okay, but if it is, let's assume it is, I'm using the z-score formula here to check for the distribution for each one. So let's run it and see. The original data set is this 918. After the z-score removal, we are back to 819. So using the z-score analysis for this very example, we will remove the potential outliers and we will come down. In other words, we have removed about 19 of the observations that are potential outliers. Okay. Somebody can also tell you that I'm not going to have a problem with it. I'm going to keep them there because I have methods, and yes, they are. I have methods that can deal with outliers. So I'm going to keep them as it is. Somebody will say that, well, I don't have time to go and take those methods that can deal with outliers. I'm removing them. So your data is reduced. So you just have to decide what you want to do. But removing them, you get this situation here. Now, let me share some thoughts with you. Oh, yes, Amanda.
Please, I've had this question. So in this case, you remember you mentioned earlier that you can have outliers and then you can have outliers which are influential.
Yeah.
So my question is, with this method, is it just removing the outliers in general, including the influential ones, or how is it handled?
We have not detected influential at all. Only the outliers. So that should tell you why it might not be sensible to do that. But actually, it is doing that. And you remember we said that the potential is that it is doing 19 observations that are being removed. If you look at the number, it was 918, you're back to 899 because it took 8 from here and took this. Okay, so if you check it, 3 plus 7 is 10. So 10 plus 8 is 18. 18 plus 1 is 19. So the numbers that you got here, those variables that were problem children, these variables, when you add them together, you get 19. Those 19 are what have been what? Removed. They have been removed. And the number has come down from 918 to 899. So that's what is done after the removal. Now, like I said, I like to deal with it. It's like multicollinearity. You don't remove multicollinear variables. Sometimes you deal with it. When your house is leaking, you don't break the house. Sometimes you seal the leak. You deal with it. Unless it's a very, very dangerous thing. Right? If it is dangerous, very dangerous, then, but there are models that can handle it. Again, there are models that can handle it. So, like I said, it's not all the time that you have to remove these outliers. And I spoke about influential because in a regression, that is when you are able to detect the influentials. But we are not doing a statistical regression here. Okay. So again, you have to bring thoughts to, to the whole point. Instead of just removing. Like I said, I wouldn't. With this one, I would deal with it. Use a better model. And I know your next question will be, what model are we going to use to handle that? That's for later. Okay, so that is it. Interquartile range can help calculate the upper and lower quartile limits to identify and remove the outliers beyond those limits. Okay. So this is the interquartile range approach that you can use as well. So this is the previous one was a z-score. Okay. So look at what the interquartile range approach did. That one removed a lot of them. The number came down after the removal. We are down to what? 701, unlike the z-score. Now, the interquartile range approach is used when the data is not normal. It's not normally distributed. So you got to make a decision. First, you got to check the distribution and know which one you want to use. And again, these are all try and error. You have to bring thoughts to what you are doing, even after you've done the analysis. Like I said, even after it's telling me to remove, I wouldn't. Okay, I'll look for what is causing the, because sometimes what is causing the problem is you go and look. In fact, I did that with somebody today, one of my students. Okay, I said, look, let's go into the Excel, the original data. Show me the data. Then when we got there, now the person herself said, look, it's true. I should have added this thing. So the person realized that there was no need to remove anything. You just missed adding these things. You should have checked the data. So sometimes open your eyes. Open your eyes. All right. That's it. Another thing you can do, okay, and this is the latter part of the something you can do, is known as contingency tables. I'll ask you some couple of questions in contingency tables in an exam. Because contingency table is before descriptive analytics, before summary statistics. Before that, you do cross tabulations. Very, very useful. Why is it useful? Because it can help you identify important linkages and patterns in your data that can further be used when you're doing further machine learning model. I'll give you 2 examples. Number 1, suppose we have, and I'll give you a couple of examples as we move forward even. Let's assume that you have the data. 1 is for those that have heart disease. 0 is for those that don't have heart disease. Now, among those that have heart disease, how many of them have asymptotic? How many of them? In fact, this is where you can bring the data. Let me just create the data set again here. Just do it here. So look at the data set now. So among those that have that, among those that have heart disease, which one of those guys are male? Among the heart disease guys, which one of them are male? Among the no heart disease, which one of them are female? Now, among those male, those heart disease patients who are males, which one of those 2 have got a resting ECG to be normal? Which one of them have got resting ECG to be LVH? So you are trying to look at classifications of things, trying to feel the rhythm, trying to understand the nitty-gritties and the intricacies of the data classes. So here's the first question we want to look at. Which sex type has a higher percentage of heart disease cases? That's the first one. You can use cross tabulation or contingency table to answer that. Which sex type? And I have multiple of these questions in your exams as well. And also in your assignment, I have that. So let's look at it. All you got to do is to take the data set here and then create a sex type, which is from this part, and then compare that sex type with the heart disease, which is the dependent variable here, the target. Okay, so it will show you how heart disease prevalence differ across male and female. Let's check. And let's see the result. It will create a beautiful table. There you go. So it creates this table for you. Remember that 1 is for heart disease, 0 is for no heart disease. You get a total number here, and you get to that. So looking at this table, who can tell me which sex has a higher proportion of heart disease cases? And you see here, I've asked you support your answer with percentage calculations. So you no problem, you tell me, we'll deal with the percentage later because of course you all know how to calculate percentage. So which one, which sex type has got a higher proportion of heart disease? Which column will you look at first? Which column will you look at first? Is it a sex column? Is it a 0 column? Is it a 1 column? Or is it all column? 1, exactly. So first, you got to go to the 1 column because that's where the heart disease is. Now, among that, which of them do you think, which of the sex type now has more heart disease? What's the number? Those of you are saying male. There are so many male numbers there. What's the number there?
458.
Exactly. 458. So if you want it in percentage terms, it will be 458 divided by something times 100. Divided by what?
Divided by 508.
Divided by 918.
I need somebody who will get confused. Is it divided by 508 or divided by 918? Is it divided by 508 or divided by 918?
508.
Ajia.
918, Prof.
Ajia. Ay. You are lost. You are lost. Somebody says 508. Somebody says 908. 999. Ay. We are dead. We are dead. Ayeka. So this is where you got to really think. Okay. In fact, by the way, if I had not brought this all part, you should have brought the all part, okay, when it is necessary. Now watch the question. Which sex type has a higher percentage of heart disease cases? The moment you go and take 918, you have included no heart disease cases. So you can't take 918. Because 918 includes those without heart disease. So it's not 918. So first you identify heart disease. And we are not talking about all males too. We are not talking about all males. We are talking about heart disease males, not males with heart disease, no. But those with heart disease, which are male, they are two different things. Okay. Because the moment you take 725, you have included females as well. I get it. So it is the first one, 458 by 508. Take note of how you get some of these understanding. It's very, very important. If it is an exam, you should know how to calculate. Let's move on. Next one. We can calculate the percentages. Okay. This one is a percentages here. Okay. So if it was percentage, you see, I didn't bring the all. And of course, you can choose not to bring the all. Okay. You will do some of this thing in your thesis, dissertation. It would be good to do that. Okay. So you can see from here that you now get a percentages. Okay. So you see that 63% of the female have got what? Heart disease. And of course, when you add the 63% to this, you get 100%. So that's why it's important to recognize this. Hey, hold on. Yeah, that's fine. Okay, next one. Which chest pain type is most frequently associated with no heart disease? Again. And then you have what percentage of patients with typical angina, okay, have heart disease? Show your calculation. So once again, you run this. This is cross tabulations. It will run both of these things. And this one will put it even in a beautiful picture. That's why I've shown the C map. And again, when you're running your thesis, you should do some of these things. Generate a C map there to bring out a point. Now it's getting deeper because I've increased the categories. So we are matching chest pain type. And remember, the chest pain type are 4 different ones. Okay. Typical angina, and then you have the NAP, you have ATA, you have asymptotic. So they are all there. And then you have the heart disease versus no heart disease. So the one on the far right are those with heart disease. The one on the left are those without heart disease. And the color shows the increasing and decreasing levels of the numbers. Question. So the question is, what was the question? Which chest type is most frequently associated with no heart disease? So which column will you go first? Which column will you go to first?
Column 0.
Exactly. No heart disease column. That's what it stated. Now, no heart disease, which chest pain type is most frequently associated there?
ATA.
ATA.
Exactly. Okay. Now, and then what proportion of patients with typical angina have heart disease? Remember, typical angina is TA. What proportion? Is what by what times what divide by what multiply by what plus what by what?
It means you sum all the ones, all the values under column 1. 20 divided by the sum of column 1.
But we know, because we know the total number of heart disease is 5 something. Do you remember the blue color? We know that here.
508.
508. Okay. So, but actually, he's right in saying that you should sum it. So even if you don't know, you just add all of them, you get that same 508. Okay, Chief, you add them. What next? After adding them, what do you do?
20 over the total by 100.
Perfect. Exactly. That's how you learn. 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 Fantastic. Now, what proportion of males? Watch this one. It's tricky and it's beautiful. What proportion of male with asymptotic chest pain? That is ASY. Okay. What proportion of male with asymptotic chest pain have heart disease? What proportion of male with asymptotic chest pain have heart disease? You can tell us.
So it means we have 3 levels now.
Oh, sorry, I think I've not shown you that.
Yeah.
Yeah.
So it's difficult to find.
So you have sex type, you have chest pain, you have heart disease. Okay. So now let's run that. So now this is the complex one of all. And you can run that also in yours. I've added the all, but ideally, normally I expect you to calculate them by yourself. Asymptotic chest pain, ASY. Okay. What proportion of males with asymptotic chest pain have heart disease? So first you have to look at which column? Which column?
Column 1, say. Column 1.
And then if you look at the rows, we have bigger rows. You have F bigger row and M bigger row. Which row?
M.
M. And then after that, you look at which of the M rows?
ASY.
ASY. You see how you match the thing? That's how you match the thing. So which number are we looking at here?
353.
353.
Exactly. And then the rest can take care of itself. It's beautiful. It's beautiful. Anyway, so this is the answer. Okay. 353. Total asymptotic males, 426. Okay. Approximately 82% of the males with asymptotic chest pain have got that heart disease. So you take that. Now that is 353 divided by 426 and multiply by 100. That will give you this number of 82%. That is how you calculate that. Okay. I think there's another question, which is based on the cross tabulation. Which chest pain type is most frequently associated with no heart disease? Check it. Okay. Most frequently associated with no heart disease. Which chest pain type? So that means you have to take the one that is the biggest here. Which one is the biggest here in the male section? 56. No, we are talking about no heart disease. Okay. The biggest one under no heart disease is 56. And which one is the biggest one here? Under male. 93. Okay. So you got those two to actually guide you. So here, where is that? Is that one we are looking at? Let me see. No heart disease. No heart disease. Oh, okay. So that's another question. Not this question. No, we've done this one already. Which question? It looks like I'm giving an answer to a question I didn't ask the question. It looks like I missed the question. But let's watch this. Males with NAP. Where is that? Males with NAP is 66.
6.
It looks like I didn't ask the question, but I had a question in mind. Okay. But the key point is that you should be able to know how to manipulate all of it. Males with NAP is 66. Okay. Males with TA is 19. Yeah. I think I asked the question by combining NAP with TA. Okay. So I expected you to calculate the NAP for males and then TA for males. Okay. And then you add the two to get 85 here. And then the total number of heart disease patients, because we are looking at the heart disease, is 508. And so you now take these two and then divide it by 508 and multiply it by 100. I think the question was about this. Approximately 16% of all individuals with heart disease are males with NAP and JF. I think this was about a question. Look at it. I think I didn't pose the question, but it's here. That how many individuals with heart disease are males with NAP or THS pains? You go and think through about it. Now, the word or here means what? What symbol is or? What symbol?
Addition.
It's addition, exactly. That's why you added them here. And then you'll be able to get the final. Very good. Cross tabulation is exciting, but sometimes can be slightly confusing. But just take your time and have a feel of each one of this. Finally, the last
Please,
one.
Yes. You say the or is an inclusive or?
It's addition, add.
Okay. Usually, maybe if you bring the and, it will be more appropriate for some of us.
No, and is multiplication.
Okay.
Yeah. And if you know a bit about the Venn diagram and sets, you know, and is intersection. Okay. And then you add that intersection to the addition. But the or is actually addition. If I say A or B, it means all the elements of A or B. But if I say A and B, I'm looking at the intersection.
So the or, we have inclusive and exclusive or. And usually the inclusive or, we make it or stroke and.
Yes. So or is inclusive.
And when the or is standing alone, it is purposefully exclusive.
Okay, what do you mean by is standing alone?
So we have inclusive and exclusive ors. The inclusive or will add the NAP and the TA. The exclusive or will be a mutually exclusive NAP or TA.
I agree, but here, why will you get mutually exclusive NAP or TA?
As it stands now, it's a mutually exclusive NAP or TA.
Yeah, so
usually when it is inclusive,
that's what I'm saying.
So okay, let's continue, sir.
Yeah, you can't get it. It's just exclusive, so you got to take them individually. That's what I'm saying. All right. So let's go to the final one, which is summary statistics. It's something you know already, but there are some 3 things I want you to take note of summary statistics. Number 1, the mean, the median, the mode. When they are all the same, keep note. When they are all the same, the data is normally distributed. Sometimes it's called symmetric. When the mean, the median, and the mode are all the same. Now, when the mean is bigger than the median, you have a long tail on the right. When the mean is less than the median, you have a left skewed. These ones you know already. These ones are undergrad, okay? So there's no problem with that. But sometimes it can be very, very misleading to use the mean. When is that? Answer. When the data has a lot of outliers, mean is not useful. Why? Because mean looks at the center. But not just the center, it brings everything together into the center. So if that everything, one of them is an outlier, that outlier will influence everybody. Take an example like this. Suppose I have 1, I have 2, and I have 18. And then I have 1, I have 2, and I have 3. Now, when you calculate the mean, are they the same for these 2 data sets? Are they the same? Are they the same?
No, sir.
They are not. When you calculate the median, are they the same?
No, sir.
Yes, sir.
Good. So the median are the same, but the mean is not the same. So the mean will be misleading because 18 is going to punish the first data set. 18 will drive all the means to itself. If you like, you take this and calculate the mean. The mean will be 1 plus 2 plus 18, okay, divided by 3. That will give you 7. 1 is not even closer to 7. 2 is not even closer to 7. And even 18 itself is not even closer to 7. All of them will disagree with that mean. But if you take the median, okay, the median is only one middle guy. And that median is, look, the mean here, the mean for the first data set is 7. Okay. The mean for the second data set is 1 plus 2 plus 3, okay, which is 6 divided by 3, and that is 2. So the mean here is 2. This mean will be agreed to by 1, because 1 is closer to 2, by 3, 3 is closer to 2, by 2, 2 is closer to 2. But then these 3, all of them will disagree with that mean there because of what? Outlier. So when there is an outlier, the mean is not a good representation of the data. So median is useful. You're not communicating. So use the median. That's why when those of you dealing with a lot of financial data, be careful. Be careful. Be using the mean and the median at the same time. Don't just use the mean. And also be dealing more with the kurtosis and then the skewness, because the standard deviation and the variance alone are not enough. Take note of that. Because the thing about the standard deviation, okay, is that it can reflect volatility or uncertainty in the data set, especially, like I said, those dealing with highly volatile markets, stock market, disaster events, and all of those things. So check that. Now let's finally check the distribution of the variables. All of them. Okay. Or maybe 2 of them, but all of them. Okay, so I had a typo again for this because I had picked the numerical columns, but I have not defined the numerical columns. So I'm just supposed to define the numerical column because I just want to plot the distribution, but I want to plot the distribution of the numerical columns and not of this. So again, you take that error, like I've always been telling you, take that error, seek support for that error, and then you get a corrected version of the error, that you are supposed to do it. And once you sort it out, drop that. So I just want to sort it out again and see. Good. So it's giving me for every variable. So this is the code that's supposed to be. So for every variable, you're able to see the distribution using the kernel density plot. The smooth curve is called KDE, kernel density plot, for each one. Look at the kernel density plot. If it is smooth, okay, and there are no peaks, then we are getting towards symmetry or normal distribution. Now, if you look at most of them, they are not smooth. This one seems to be having some jagged point here and another peak here, reflecting possible multimodality, or in this case, bimodality, meaning there are 2 modes. Now, if you look at this, there seems to be one mode there and another mode there, again, representing a possible bimodality. This one, you don't even know what it is doing. This one, there are 2 modes clearly. It's not normally distributed. And then the same thing. This one is a multimodality, multiple modes that are being exhibited. Okay, so there's a lot of skewness there. So here's a question. What does a skew distribution tell you about a feature like cholesterol? Okay, do I have cholesterol here? It looks like I didn't have cholesterol. Oh, there's it. There's cholesterol. So when you take cholesterol here on the top right, okay, what do you notice about it? Most of the values cluster on the left, few extreme values. The mean is bigger than the median. The mean cholesterol level is inflated by outliers, and you can see that the median better represents the average person than the mean. And so it violates the assumption of parametric tests. Parametric tests are used, we'll look at that next time. Parametric tests, you use them to do analysis when the data is normally distributed. Okay. By the way, when we say normally distributed, it's nothing more than similar. Mm-hmm. Like most of you, your ages are normally distributed, which means most of you are around the ages of 25 to 35. Can I say that? Can I say that most of you are between 25? You know, so there's an outlier among you. The moment I know. There are some outliers among you. The moment I say that, the person is sitting there. Talk about what you so that person will not the person will not agree with me. But the majority of you should not have that problem at all. Okay, so finally, you can compare the box plot of age by heart disease. Let me show you that. These are just a few distributional analysis you can do. So I have no heart disease and I have heart disease for age, okay, for age. So look at heart disease and look at the ages. The ages are on the axis. What can you say regarding older people? So first of all, look at those with heart disease. What can you say about their age compared to those without heart disease? This one is a final one. Anybody can tell. What can you say? I mean, give me your prior knowledge. What does that tell you? This is heart disease. So the heart disease one is this one here. What do you see about their age? Their age is the middle one. That's a median age. Okay? And this is a median age here. So what can you say about the ages of those with heart disease?
So heart disease increases with increasing age.
Say that again.
Heart disease increases with increasing age.
Thank you. Finished. The older you get, the likelihood of you getting heart disease. So age matters. Age matters. Fantastic. That's how you think through. But you see, by just using the graph, you're able to get a picture of that. Okay. And the details of all that I've also documented here. Ladies and gentlemen, oh my goodness, that brings us to the end of the entire caboodle. We use this data to do logistic, random forest, ADA boosting, or all of those, binary classification analytics, support vector machining. Okay. And then we use another data set also for regression techniques, like all of this. But this is just key. This is key because these are data processing and EDA are very critical as the beginning point of your work. Any question? Ladies and gentlemen, that brings us to the end of the entire caboodle. It's been a pleasure having all of you.